So there's creepy screen. So we've got some stuff to do today. Already in week 6, already in October. So we've got another quiz to go over. Homework 2 is out and due next week, so I'll answer questions on that. And just to point out, I will not be here a week from Thursday, so you get another day off. I will be in lovely Baltimore at a conference. And you'll be there too, right? Are you excited for lovely Baltimore? No. I heard that the aquarium is worth going to. Can anyone second that? No? Any other travel tips for Baltimore? No?
There are certain districts that you don't want to go.
Okay. Travel untips, as it were? Okay, well, we'll talk about that then. But let's do our quiz first. So just as a reminder, these quizzes are graded for effort, not accuracy. And I also don't pay attention to how long it takes you to edit these. I don't keep track of any of that info. The idea is for us to give a structured review. So first question, what is the difference between the model for the means and the model for the variance? What goes into each? What's the model for the means for? We'll start there. Predicting values, so fixed effects of predictors that you know. So the questions for the model for the means would be, which predictors should you include? Should they have main effects only, or should they interact, etc., etc.? So the focus is on creating predicted outcomes, usually to test hypotheses about the unique effects of the predictors. What about the other side of the model? What's in the model for the variance? Random intercepts. What else? I'm sorry? Group is a level, and it would have a random intercept, yes. What about people? What do they have? Yeah, residuals. So the model for the variance in general is how you describe the variability and covariability across your observations. So in a 2-level model we've been talking about, you would have a group level random intercept, and you would also have a person level or within group residual. And why do we care about that? What would be the harm if we left out the group level random intercept and just used regular old regression? Errors are not independent, yes, and what's the problem then that we would be making? How would that show up?
Didn't we say it's like treating everyone as one group? Like if you're...
Yes, in the single level empty models thought you had one group with all the people in it, yes, so people would be assumed independent. But how would that affect the results of your models?
It's easier to make typo.
Standard errors are going to be messed up. Yeah, standard errors come from your model for the variance. So they can be inflated or deflated if the wrong variance term is used. And in a single level model, there's only one variance term instead of at least 2. So it's not necessarily that the fixed effects are incorrect, it's that their standard errors are. So we need the model for the variance so that we can believe what comes out of the model for the means. That's the idea. All right, next question. All the words, yeah, sure, go ahead.
I think it's a little bit off topic, but when I was reading a paper, sometimes people use a fixed effect to kind of analyze a longitudinal data, saying how changing X predicts a changing Y.
Yes.
And people call it a fixed effect model.
Yes.
How could I interpret why people call it fixed effect? What's the difference between from the kind of regression? I understand it's predicting a change, but I still have a little bit difficulty why people call it fixed. Then what's random? So
Okay, so yes, based on what you're telling me, I'd have to look at it to be sure, but what I think they're doing is they are taking the dependency caused of occasions from the same person, and they are controlling for it by putting in person as a fixed effect instead of a random effect. So what happens is they literally put in person ID variable as a categorical predictor, like they dummy code for each person, and that controls for intercept differences between people, and they'd have to interact person ID with any of the predictors as well to control for slope differences. And they do that instead of fitting a two-level model, because persons can either be a random intercept or they can have a dummy code as a main effect of ID.
So it means like these are kind of like not control, but like kind of drops like fixed part in terms of longitudinal.
Yeah, they are, I think it's, let me see if I have a slide on that in this one. Yep. This. So two ways of addressing dependent observations or correlated observations. The same level 1 units within a level 2 unit, they did the top one. So by putting person ID in as a fixed effect, then they don't need to have a two-level model. So then occasions are functionally independent because they've controlled for the dependency by putting in which predictor is which. So that is a viable thing to do if you either care about the specific people. So like, let's say that you're a therapist and you're tracking your patient's progress, and you really want to know like how Huey is doing this week. And so you want to know about Huey's slope and Huey's reactivity to this, then putting in a Huey fixed effect, a dummy code for whether or not it's Huey and 0 for everybody else, would allow you to track that person. The other reason you might do this is if you didn't have that many people. So if they're pooling data, say where they only have like 5 people, and they just want to estimate a model on a combined data set, putting in 4 contrasts for the 5 people then would control for person. But fixed effects do not allow you to predict why some people are higher than others or change faster than others. And so that's why it's a less flexible approach in terms of addressing hypotheses about multiple levels simultaneously.
Oh, okay. So like I see, because each person is like treated as a fixed effect.
Yeah, the inference is about those specific people as opposed to a random population of all the people that could be there.
Okay.
Yeah.
Thank you.
No, that's actually not off topic. So in that case, they are estimating a single level model because they've controlled for the second level via fixed effects instead of random effects. And that's fine, it's just inflexible when it comes to testing hypotheses about the level 2 units. All right, that makes sense? Speaking of level 1 and level 2, vocab. Give me all the words that you can think of that go with level 1 or level 2, and I got a few started here. So in Snyder's and Bosker, they use words that start with M to describe level 2 and level 1. Micro, macro. Yeah, which is which? Which one is level 1? Micro. Level 2 means macro. Nesting word. So between or within. Which one's within, which one's between? Level 1 is within. Level 2 is between. This always holds no matter what kind of study you're talking about. So if we have clustered data of persons in groups, level 2 is between groups. Level 1 is within groups. If I had a longitudinal study like he just asked about, then it's between persons and within persons. So these adjectives always apply. The only question is what they're referencing. Good. Type of variability. Words that start with an I. Inter and intra. Which one goes on level 1?
Inter.
Intra.
Take a vote.
Inter.
Inter, intra. Which one means within? It's on that one. Between is inter. Yeah, intergroup variability versus intra-group variability. Yep. Symbol in the model. So the variability at level 1, what symbol do I use for that? In the equations. Nope, that's a placeholder. E, yeah, E. See also R in some people's books, but E is what I use. At level 2, I say U, actually, yeah. No, I picked letters for my book and for my class based on what I can reasonably draw or type. I never picked like squiggle 1 or squiggle 2 or any of the other Greek letters that are really hard to find. So yeah, it's U. Yep. More generally, a U is known as what? Starts with an R. So we'll say random effect is sort of the general umbrella term, where you can have an intercept and you can have a slope. U0 is an intercept. U some other number will be a slope, most of the time. And what do I call E's then in the level 1 model? Residual, yes. So level 1 model for the variance captures micro variability within groups, intra-group variation, using E to represent each one, calling it residual variance. All of those go together in your head. Welcome, Dr. Aloe. Level 2, macro units, between groups, intergroup variability. So far, we only have one, U0, which is our random intercept, but starting next week, we'll have random slopes too. Can you think of any I forgot?
I have a question.
Sure.
Is there any real life scenario there is only random slope, no random intercept?
Very rarely would that be the case. And it would make me very squishy to do it. So yeah.
I just read a paper using that model.
Using that model?
Yeah, fixed intercept but random slope.
Fixed intercept and random slope. What was the context in which they decided to do that?
I can't remember.
Okay, can you send it to me?
I'll send it.
Okay, yeah, I'll take a look at that. All right. Other questions? Okay, and then let's see. Third question. In a 2-level model for persons nested in groups, how would we calculate and interpret an intra-class correlation from an empty means random intercept model? It's a ratio. What goes on the top? Intercept. So putting this here, it's the ratio of U0 variance over what? Residual and this, so it's total. So intra-class correlation has 2 alternative interpretations. It's the proportion of what? Variance between the groups due to mean differences specifically, because it's an intercept. Yes. It's also the correlation of people from the same group. Very good. Now, why would this be useful to know in guiding future data analysis? Let's say that my intra-class correlation is 0.8. That's not good. So it's not good if you want to do what?
Make statements about the differences between, because basically everyone's pretty much the same person. Not quite as an outline, but they're very, very similar.
Yeah, people from the same group are very similar. So it's bad news if I want to be able to predict differences across people within a group, right? Because that's only 20% of the variability. But it's good news if I want to predict differences between groups. That's 80% of the variability. So it gives you a sense of what's going to be relatively more useful. Good.
So, sorry.
Yeah, please.
I just wonder, when we report the ICC, should we report both intra and inter-ICC, or only one ICC? Because I know the larger, the more differences among groups, and the smaller is the other.
You can do both if you want to, although that might be, what I wouldn't do is give one and then define the other. So like I would say it's 80, the ICC is 0.8, indicating that 80% of the variability is between groups, and then I might say, and 1 minus 0.8 equals 2 is within groups.
So it depends on what research question is, because you want to explore the differences between persons or among groups, right? Depends on what the research question is. But for the multi-level modeling, you're supposed to find the differences among groups, though.
So long as your interclass correlation is not 1, then you can look at person things. So long as it's not 0, you can look at group things. So anything between there, you're good to go for either level of variability and prediction. Okay, any question? Shinji?
Yes, so because ICC is like a variance, like it's a percentage of variance, like
Yes.
derived from between, like when thinking about mean of each group. So it means, let's say, for example, like actually like we have a few groups as a level 2, and like they have a very different slope, but actually their means are like same.
Mm-hmm.
So in that case, like our ICC would be 0, even though like each group has actually very different slopes.
Yes.
So it means like we may get a very like insignificant ICC, like in terms of like fixed slope model.
Mm-hmm.
But like if we do like maybe random slope model, actually we have a very different result. So
Yes.
like, so it's like if we rely on ICC, like we may have a little chance to overlook like those like very important like a random slope model.
Yes. So the ICC from an empty means model is not controlling for any predictors. So it can be 0 and then come back higher if residual variance at level 1 is explained, because the two are yoked together. It can get higher. But then it's also, in that case, it would be misleading to think that there's no group differences at all. That's why I'm trying to clarify the ICC is group differences in the mean specifically. What would happen is that if you do have random slopes, that necessarily implies that group differences would grow or shrink as a function of the variable that has a random slope. So like groups might be not very spread out at one point, but then they spread out further at another point. And so there's no such thing as the ICC in that case. The ICC has to be like the ICC for x equals 1, the ICC for x equals 2, and it's conditional in that regard. But yes, good point. Other questions?
I have a question.
Please.
I'm wondering, so what happens if your data is like very similar across people and across groups? Like just everyone across the board is like very similar. Would that show up in the ICC?
The ICC would take into account the scale of the variables, and so that you wouldn't have very much variance in an absolute sense in that case, but it would still be important to know relatively how much is at level 2 relative to the total. So the numbers could get super duper small. In that case, you might want to rescale the outcome so that the numbers are bigger to avoid numeric imprecision issues, but I think it would have to get pretty extreme before that would be a problem. Okay. Other questions? Okay, last one, setting up where we're headed next. In a 2-level model for persons nested in groups, what is the role of level 2 predictors? What are they for?
To capture similar across the people? To capture predictors that are similar across everyone in a group?
They would have to be identical to be a level 2 predictor. So group characteristics is what we're talking about. Those are level 2 predictors. What do they do?
You mean like tell you where your people are from, like if it's a school level?
What would be the purpose of including them in a model? What kind of variability would they capture?
If it's like a school, then differences in population of students that come from that school. So if the school implements a technique that the other one doesn't, that wouldn't show up if you didn't include.
If you have a school level characteristic, so if I have students nested in schools and I put in like whether the school is private versus public as a school characteristic, what kind of variability would it account for?
The variance comes from the group level.
Yeah, there's a reason I have this highlighted, right? This one. Why are some schools higher in their means than other schools? Maybe it's because some of the private schools are higher or lower than the public schools. So putting in level 2 group level predictors is supposed to explain why some groups have a higher mean than others. That's this variance that should come down. Do you remember what it's called when we calculate how much reduction in one pile, one variance component you get? What kind of R-square is that? Pseudo. Yeah, and that's not me being funny, by the way. That's really what it's called. Pseudo R-square, because these things are squishy and they can move around, particularly in unbalanced data. So group level, level 2 things predict why some schools are higher than others, which reduces this U0 random intercept variance. Put the 0 there. That means, what's the role of person level predictors? Yeah, explain the within level variability, the residual. Why is it that some people are higher or lower than everyone else in their school? Because of their own characteristics. And that should explain level 1 residual variance, and that's where we're headed today. Okay. Questions on any of that? Yes?
So, for example, when you have these ones, they are all because you've already given us the predictors, which one you want to the one you want to do, but in the real world, so you have to distinguish on your own. For example, you analyze the data set, you have to study if, for example, this predictor is constant over persons, and then if it is constant for persons, we may consider as a level 2 predictor or level 3 depends on. So, and otherwise, if you just capture all the differences among people, we may just automatically go into the level 1 predictor. Is that, I mean, in the real world, right?
In the real world, if it is not exactly the same across everyone from the same group, it is a level 1 predictor. Level 2 predictors are group level things. They cannot fluctuate within groups. And so if you're not sure whether what you have, you can calculate the variability of a predictor for each group or across groups and see if it's 0. If it's anything, then if there's any variability across scores within a group, it has to be a level 1 predictor. If there's variability only between groups, no variability within groups, it's a level 2 predictor. And the software knows what you have because it's doing this behind the scenes to figure it out. So like in SAS and Stata, when you enter predictors on the model line, it figures out which is which. And that's actually part of the problem because the computer is very happy to do exactly what you ask of it, even when you ask it to do something dumb. So that's a beautiful segue. Level 1 predictors. So last time we looked at a couple examples of level 2 predictors. For instance, a model that looks like this, if we have public versus private and school size, as school or group level characteristics in this example, we can put them straight into the level 2 model predicting the intercept. Each school gets a differential intercept prediction based on these. U0 is then how far off each school's real intercept is from the one that's predicted by these fixed effects. Cool, right? Just stick in the model, make sure it's centered so that 0 means something, but otherwise we don't worry about it. Level 1. This is the number one thing I see people screw up in multi-level models. And not just novices, people who should know better. So I challenge you to go to any journal that you're familiar with and look up a study that uses multi-level modeling. I almost guarantee you will find one of these errors. That's how common it is. So putting in a level 1 predictor as is. So for instance, let's say that I have math scores I'm predicting from amount of time that a parent spends reading to their child. And I've centered it so that 0 is the grand mean of this variable. And I put it in my level 1 model. So math per person within a group is a function of a placeholder for the group-specific intercept. And in this case, we're not putting any level 2 predictors in yet. So each group's intercept is the fixed intercept, gamma 0, 0, which is the grand mean of the group means. Plus Z0 is how far off each group's intercept is from the fixed grand mean. Then we pick up another beta placeholder. So beta 1G is a placeholder for what's going to be the effect of student reading. Each group potentially can have their own, but for now, they don't. They all share one fixed effect. So because we're predicting beta 1 in the level 1 model, everything in this beta 1 equation would have a 1 to start with. And 0 is the jumping off point for what the fixed effects would be. The next one would be 1, 1, 1, 2, 1, 3, and so on. So this model looks fine, right? We get a fixed effect for the effect of reading. We go about our business. The answer, as you might have guessed, no. This is very, very, very likely to be broken. And I've heard people try to argue with me that it depends on your theory. No. No one's theory says, I would like the wrong model, please. No. Here's the problem. Level 1 predictors are most of the time actually 2 variables in one. So for instance, amount of time parents spend reading to their children as our example level 1 predictor. Within a school, some parents spend more time reading than other parents. That's within group or within school variation. And some schools are characterized by more attentive parents, where all the kids in the school have parents who read a lot, or none of the kids do. The idea is that just like we would have to worry about the multi-level nature of the outcome, the whole reason we would do a multi-level model for math scores of children that are nested in schools, we have to worry about the levels of variation in the predictor as well. And just as we can do for an outcome, we can quantify how much variation we have of each kind with an interclass correlation from an empty model. So if your interclass correlation for your predictor is greater than 0, then you have between group variation in your predictor, and that between group variation can have a level 2 effect. I'll say that again. If your interclass correlation for your predictor is greater than 0, then you have between group variation in your predictor. That between group variation can have a level 2 effect. If your interclass correlation is less than 1, then you have within group variation in your predictor, and that within group variation can have a level 1 effect. So to the extent that groups differ from each other in your predictor and people differ from each other in your predictor, that's 2 different predictors, not 1. And it has to go into the model that way.
Mean center then?
Mean centering doesn't change the variability. It would just shift the fixed intercept of the variable to be something other than a different number. So the idea that we would have grand mean centered this variable doesn't solve the problem. That just shifts it over on the x-axis. So it is possible for these level 1 and level 2 effects to be in the same direction or in opposite directions. So if you think about the relationship between socioeconomic status, SES, and achievement, it may be that schools that have more money than other schools, they're filled with children from rich families, they may have higher achievement than other schools. So that is a between school effect of socioeconomic status. Within a school, if you have more money than your classmates, you might have better achievement too. You might have access to tutors or people to cheat on your SAT for you or what have you. So SES leads to achievement in a positive direction in both of these associations. Here's an example of associations in the opposite direction that I borrowed from another paper. Body mass and life expectancy. So larger species tend to have longer life expectancies than smaller species. So whales live longer than cows, cows live longer than ducks. But within a species, fatter animals have shorter life expectancies than smaller animals. Both of these things are true. So if I asked you, what is the relationship between body mass and life expectancy, you'd have to say, which one? There's a level 2 relationship between the groups and a level 1 relationship within the groups. So to the extent that body mass varies between animals, between species I should say, and within species, and to the extent that life expectancy varies between species and within species, there is the potential for a level 2 effect and a level 1 effect, and they don't have to be in the same direction, and they certainly aren't going to be of the same magnitude because they're unstandardized coefficients on different scales. So the only situation in which these 2 effects would be on the same scale is if X and Y both had the exact same interclass correlation and they were both standardized to be the same variance. Then there is a potential for the effect at level 2 to be the same as the effect at level 1, but that seems pretty unlikely because they're theoretically different constructs as well as variables on different scales. So every level 1 predictor, to the extent that it has level 2 variation, to the extent that its intra-class correlation is greater than 0, we got to worry about a separate level 2 effect in the model. So this is what you get when you don't. I'd like to introduce you to a new vocabulary word. This fixed effect of level 1 student rating is what's known as a smushed effect. That's my word. I put it in my book. I put it in the index of my book. I am trying to make it a thing. I say smushed because it's like you took the level 1 effect, the within group effect, the level 2 between group effect, and you just smush them together. And you come up with one number. So it's a weighted blend of what should be 2 separate numbers. If you are uncomfortable saying smushed effect, here are some synonyms that you can use. A convergence effect, conflated effect is probably the one that I like second to that, or a composite effect. It's the idea that it's a blend of 2 different things. Yeah.
So under what scenario does this equation work?
This equation would work.
Because like based on the equation, I can see that different groups, their individual regression line is parallel to each other. The only difference is the intercept. So what kind of reading can generate that kind of pattern?
The only situation in which this model would be appropriate for sure is when the intra-class correlation for this level 1 predictor is, what do you think, 0 or 1? Take a vote. 0? A couple people voting for 0. 1? Abstain? It's 0. A 0 intra-class correlation means no between, all within. So if you have a level 1 variable that only has level 1 within group variance, then the only kind of effect it can have is level 1 within groups. And this is not a smushed effect, it's the level 1 effect. That's the only time then this you can be sure this is okay. That pretty rarely happens. Now the pictures that you have in your head, I have pictures for you, what this would look like. And I think they're coming soon, soon-ish. They're not next. But I have diagrams. Here, what the heck? That doesn't look right. There we go. Diagrams for what this looks like. So we take our original variables, y per person per group. The first thing that we do in an empty means model is partition the variability of this original variable into what is level 2 between groups in the intercept and what is level 1 within groups and residual, right? So now it's functionally, we have 2 different variables that we're using to represent what used to be 1. We're letting the model figure out their variability, but you can think of these as latent variables in a sense that we don't have observed versions of them. In contrast, on the x side here, we've taken this original variable, perhaps we've mean-centered it so that 0 means something. That's irrelevant for this discussion, whether it doesn't change anything. But we're assuming that its one effect applies equally in predicting level 2 variation and equally in predicting level 1 variation. The smushed effect has to do the work of 2. So the way that we fix this, let me see, what that smushed effect is, by the way, people smarter than me have figured out, and it is weighted by the precision of the fixed effect at each level. So it's going to be between group effect divided by the standard error for that, plus the within group effect divided by the standard error for that, plus over the same sort of information on the bottom. So what happens in practice, level 1 is typically way bigger than level 2 in terms of sample size, right? Like if you have 10 kids per 30 classrooms, that's what, a sample size of 300 kids I'm doing math in front of you. Does that sound about right? So 300 kids versus 30 classrooms. 300, any fixed effect belonging to 300 is going to have a much smaller standard error than any fixed effect belonging to 30. So the smushed effect, the convergence effect, is going to get pushed to be closer to the level 1 effect, which means it's the level 2 model that is all screwed up. Level 1 will be mostly fine. It's level 2 that becomes the problem. By the way, the paper that you mentioned, Shinji, about using fixed effects, I bet they use this word in there somewhere, the endogeneity problem. This comes out of the econometrics literature and other places where they believe that fixed effects models are better than random effects models. There's a recent paper that should be coming out in, I want to say, Psych Methods that I served as a reviewer that explains this. Smushing is the problem of endogeneity. So the only reason that you should prefer fixed effect models over random effects models is if your random effects models are smushed. So paying attention to this solves that problem too. So here's 3 different ways that we can solve the problem of estimating smushed effects for level 1 predictors. The first 2 rely on brute force variance decomposition through observed variables and are the only option within univariate multi-level modeling programs such as mixed in SAS and Stata. We can do group mean centering to create a new level 1 predictor, or we can leave the original level 1 predictor in. This is the second way is much more common in cluster data, but it's much easier to screw it up. So I'll just tell you, I prefer number 1 almost always. This makes the most sense. It's the easiest thing to do correctly. If you are able to leave the world of univariate MLM and accept that your x's should be treated the same as your y's, that gets you into the world of multivariate multi-level models, or what some people call multi-level structural equation models. And in that case, you let the model partition the variance in x the same way you do the variance in y. I hope that we will have time to get to those models later this semester, but it requires switching software packages. So here is the first option, my preferred person mean. No, not person mean. Wrong class, excuse me. There. Group mean centering. We're going to take our level 1 predictor and literally carve it up into each level by itself. So at level 2, we're going to take the mean of the level 1 predictor across groups, so x bar, and we're going to subtract a constant from it so that 0 means something. I don't care what constant it is, that's just to keep the intercept meaningful. Let's say that we choose the sample mean for the predictor. Then a high value of this GMX would be a group that has more of it on average than other groups. A low value would be a group that's lower on average. So the individual level predictor, such as reading in this case, becomes a group level characteristic. It's a summary across the individuals in the group. It now belongs to the group. So this would be like a high reading group or a high reading school versus a low reading group or school. Within groups then, we are creating a purely level 1 reading predictor. So within group X, for each person within a group, is whatever their original predictor value was minus the group's mean, the uncentered group mean. So now, there's only level 1 within group variation. This new within group predictor is orthogonal to the group mean predictor. So within group 0 means I am at whatever the rest of my group is on average. Within group positive number, I am higher than everybody else in my group. Within group negative number, I am lower. So now each of these goes into the model at its own level. Within group is purely relative to your own group because what your group is captured at level 2 where it belongs. So the new model looks like this. Question or stretching?
I will wait.
You're going to wait, huh?
You may get that. I will.
Fair enough. So it's been fixed. So rather than putting the original reading predictor in, I'm putting in the 2 new variables that I just created. The level 1 predictor is this new variable that contains only within group level 1 variation. Because that's the only kind of variation it has, its fixed effect in the model can only be the level 1 within group effect. So it's been unsmushed. At level 2, group mean X only has level 2 between group variation. So the only kind of effect it can have is a level 2 between group effect. So that's gamma O1 in the equation for the intercept beta 0. That becomes the between group effect. So you put it together, gamma O1 right here at level 2 is the effect of being from a higher group. Gamma 1O at level 1 here is the effect of being higher than the rest of your group. Two different predictors, two different jobs, two different levels. Okay. How are we doing?
Still again, so for the level 2 group mean, and then I noticed that you have a constant, so, but still in the real world, how did you know what constant you should use, and then what rationale behind this?
I run descriptives, I figure out what the mean of the variable is, I pick something near that. Any constant is as good as the next. The only time that it matters is what your fixed intercept becomes, and if you have interaction terms, making sure that the main effects that reflect the zero value of the interacting predictor, that those are not nonsensical. So there is no wrong way to center with respect to the constants. The problem is putting in one variable in the model instead of the two that actually should be there. That's the real problem.
So then you need to put both in order to get the best results, which means the between and within.
Yes, because
So you can't just use one randomly.
so in this
Not randomly,
So in the specification, leaving the other one out means the same thing that it normally would. If you leave a predictor out of a model, what are you assuming about its fixed effect? 0, right? So if I leave out within group reading, I am saying that me reading more than anyone else in my school doesn't matter. If I leave out between group, the group mean here, then I'm saying that going to a school with more readers doesn't matter. Now that one is a little bit weird because it's weird to me to think of the idea of relative being in the model but not what it's relative to. Because within group X here, this is more or less than your group mean. That's what it means. To me that only makes sense if the group mean is in there too, but it's not technically wrong because if you leave it out, the thing you're leaving out you assume is 0, the same as usual.
So do you mean if you have a large scale data set, you will have a lot of predictors, and then how do you know, for example, like SES is the one example you mentioned, but in the world, maybe they have collected a lot of different, like reading is another. So a lot of predictors, but when do you know if you need to group me and then to within me? So you do have to do all of them? There's a lot of hassle.
Yes. Any level 1 predictor that has level 2 variance in it needs to become 2 predictors. So Tiongping, your question, like when would the other equation be okay? Think about this. If the variable really only varied across students, but on average it was the same across schools, then that variable right here is not a variable, it's a constant. If groups don't differ in their level 1 predictor on average, there's no information to put here.
So it becomes like it's not even multi-level.
Yeah, it's not a multi-level variable anymore. It's a purely level 1 variable. So we have, through brute force, partitioned the original variable into its level 1 part, which goes in the level 1 model, and its level 2 part, which goes in the level 2 model. We did so ahead of time so that we know exactly what the effect of these variables means because of the way we built them. That's why it's the easiest to not screw up. Because no matter if you put it in or leave it out, you know what the other one's going to be. The other way of doing this is not the case. Do I have a picture next? Yeah. This is what we've done. So we have done the observed variable version of what the model is trying to do on the y side. The y takes the original variation in y and splits it into how much is level 2 between groups. Intercept, right? Intercept is mean, right? And how much is level 1 within groups. We built new observed variables to capture what is between groups in intercept, in mean, and what is within group deviations around those means. So then the level 2 between group effect is carried by the group mean. The level 1 within group effect is carried by the within group deviation, and everything is cool. Unless you're saying, why are we doing observed variables on one side and latent variables on the other? And I'd say, good point, put a pin in it. That's multivariate, multi-level models, or multi-level SEM, in which these become circles too. All right, did you want to ask your question yet?
Can I ask you 2 questions?
Two questions, oh boy.
Hold on.
All right.
By now I have 2. I see many people to aggregate the level 1 variable to the mean and use that as a level 2 predictor.
Yes,
So
that's what we're talking about.
Huh?
That is what we're talking about so far.
Yes. How you handle it if you have a dummy variable at level 1? You will still center in it?
Yes.
Okay.
Then that situation, so in terms of making a level 2 mean, then it would just be each group would be the proportion of 1 values, which you can still think of as a level 2 predictor. Then the idea of group mean centering a binary variable is a little weird,
Yeah.
because you would end up with like a value of like, maybe 0.3 or, minus 0.7, which can't happen. And that would be a situation in which you would want to go this route instead,
Okay.
which is where we'll head next. But probably not today, so you may have to come back again.
Come back.
Okay. All right, was that 2 questions or 1?
I think there was 1, but I saw that there were 2, but it was 1.
Okay, we're good?
Yeah.
All right. Other questions? 1, 2, or 3? Take your pick. No? All right. Let me see what's next. Pictures. Yeah. So let's look at the pictures. That's what's right. So this is what group mean centering will get you out of the model. You have the group mean at level 2 across level 1 units as a new predictor. That goes in the level 2 model. If it's significant, it should explain level 2 random intercept variance. Within group effect, that goes into the model as the deviation of each individual around their group's mean. If that's significant, that explains residual variance. So here's what it might look like in each of these situations. Let's say that we have student reading on the x-axis, we have student math as the outcome on the y-axis, and I've got 3 different lines for 3 different types of schools here. The red line is for a school that has mean reading of 4, green is for 5, and blue is for 6. If I had a result in which the effect of reading on math was solely between schools, between level 2 effect only, it would look like this. The level 2 fixed effect is given as this yellow line through the means here. This picture was made by generating a slope of 1. So for every 1 unit higher school mean reading, school mean math goes up by 1. Within a school, the within school slopes are flat. That fixed effect is 0. If I read more than my own school's average, that doesn't help me in my own reading. So it's between schools only, not within schools. Here's the opposite. See? Camera 1, camera 2, camera 1, camera 2. Now this is purely within, no between. On average, for every 1 unit higher mean reading, your school's math doesn't change. The slope for the level 2 effect through the school means is 0. Within schools, though, if I do more reading than everybody else, my math is higher than everybody else's. Could be a little bit of both. So in this case, the between level 2 effect is 2. For every 1 unit higher school mean reading, school mean math goes up by 2. The level 1 within school effect is 0.5. For every 1 unit higher reading than everyone else, my math goes up by 0.5. So this is a situation in which if you estimated a smushed effect, it would be drawing like one line through all of this. That would be a little bit steeper than the within line, but not nearly as steep as it should be between. So the smushed effect would probably be something like 0.6. It would be mostly the within effect, pushed a little bit towards the between, because it's a weighted combination. But it doesn't describe what happens within groups or between groups. So it's a useless effect. All right. Do you want to see an example? Yeah. I appreciate your enthusiasm, Molly. She's always the first one to say, yeah. Let's do that. So back to example 3A. We did this one last time looking at school level predictors of homework amount, 3 types of denomination and use of mixed grade classes. So now the rest of the data manipulation for the level 1 predictors becomes relevant. So language is my outcome. I am using 2 level 1 predictors, verbal IQ and performance IQ. I'm guessing that's some kind of nonverbal matrix reasoning something or another. Again, the documentation for these data is a little bit to be desired. I'm subsetting the data set to be complete for all of my predictors and my outcome. We'll talk about missing data next week, I think. I z-scored the 2 IQ variables to put them on the same scale. That way I can show you examples of how to test differences between coefficients at the same level. I then computed school level means. So I have 2 new variables here, actually 3 including the outcome. School mean language, school mean verbal IQ, and school mean performance IQ. Because it's a z-score, the mean is already 0, but I put this here just as a reminder that if 0 isn't a meaningful value in a level 2 predictor, you want to make it so. The new part then is group mean centering my level 1 predictors. So I did it for the outcome too, just so that I could run descriptive statistics to show you what happens, but we really just need it for these 2. So my variable names, by the way, the WS, that means within school. So this is within school IQ, either verbal or performance z-score. It starts with whatever it was for the original level 1 variable minus the school's mean. So the school's mean goes in the model for level 2. The within school deviation for each person goes in the model at level 1. And Stata does this with special egens instead. So school mean language, school mean verbal is egen mean by school. Okay. So then the descriptives. To answer your question, then, how would I know about these variables in the real world? Well, these are the school means. They have variability. That means that even though we're thinking of IQ as a student level characteristic, it is also a school level characteristic, same as the outcome of language. So I'm trying to quantify how much of the variability is attributable to school versus individual, So you can see the differences here, like original language and within school language. There's less variability within schools. So original variable is 8.8, within school is only 7.7 for the standard deviations. So this is the descriptive version of what the empty model is trying to do. It's trying to partition the variability in each of these things. So let's do that first for our two predictors. So we went through all of this last time. We're starting on page, what page is this? 11. Here we are. So I'm at the bottom of page 11. First question. How much of the variability in student IQ is actually at the school level? To the extent that it has variability at the school level, I have to worry about a level 2 between school effect. So I'm treating IQ verbal z-score as the outcome, estimating an empty model that has a random intercept variance across schools, as well as a residual variance for students within schools, asking for the intra-class correlation. VCORE and SAS, we'll talk next week about what that means, and SStat and Stata does the same thing. So you told me earlier today, random intercept variance, so school ID variance, 0.12, divide by the total of these things, that works out to be an intra-class correlation of 0.12. So student IQ verbal, 12% of it has to do with which school you go to. Some schools have smarter kids. Likewise, performance IQ, intra-class correlation is smaller, but still significant if we compare it to a model that doesn't have a random intercept via a likelihood ratio test, 5%. So 5% of performance IQ differs between schools. So we're going to look at the effects of these IQ variables one at a time. Because I'm using group mean centering, I don't have to worry about putting both levels in at the same time. They're orthogonal. So I'm adding IQ verbal at level 1 and the school mean of IQ verbal at level 2 simultaneously. So the model that we have then, level 1 previously didn't have any predictors in it. It only had a school-specific intercept beta 0. I am now picking up a school-specific slope, and I am showing the centering in the equation. So I think it's helpful to do this to remind people what 0 means. In this case, my level 1 verbal IQ variable will be 0 when I'm at my own school's average, whatever that happens to be. So I am relatively average. That beta 1 is defined at level 2. So as many betas placeholders as you have in the level 1 equation, that's how many level 2 equations you have to have. So far, it's just a fixed effect only. So the fixed effect is gamma 1O because it's predicting beta 1, so everything would start with 1, and 0 because it's the first entry in this prediction. So it's the fixed effect. So technically speaking, I don't need the placeholder. I could just put the gamma 1O straight up here. But I'm not going to do that because we're going to add stuff. The level 2 model from before already had 4 fixed effects in it. So fixed intercept is the expected school level outcome when all the predictors are 0. Gamma O1 is the fixed effect of school level homework. O2 is whether or not the school mixes age grades. 3 and 4 go with that denomination variable where 2 was higher than 2 or 3. And now we've picked up school mean verbal IQ as gamma O5. So school mean IQ only has level 2 variance in it. It can only have a between group level 2 effect. Our new version of student IQ that's been group mean centered only has level 1 variance in it. It can only have a level 1 within school effect. Okay. So I load those up on the model statement in SAS or the analog in Stata. And note that I don't have to do anything different to tell it that it's a level 1 predictor or level 2. It figures it out. The only program in which that is not the case that I know of, I guess there's two. There's the HLM package and also M+. It needs to know if it's level 1 or level 2, and if you get it wrong, it will yell at you. But SAS, Stata, SPSS, I think R, LME are happy to figure this out. Is that true? Yes? Okay. That's what I figured. Okay, so I'm asking for a couple pieces of extra information. One is an omnibus multivariate wald test for the two effects of IQ together. So I can answer the question, does IQ matter? Thinking about it as a composite across both levels, 2 degrees of freedom. The other one is the difference between the within school effect and the between school effect. That has a special name called a contextual effect that we'll talk about more later. But I include it here for completeness so that you know how to get it no matter which way you set up your model. The other things that I'm asking for, I'm asking it to predict outcomes using the model fixed effect so that I can calculate total R square for that correlation. And I'm also saving the covariance parameters so that I can do pseudo R square using the SAS macro that I wrote. And here we go. So I've got my two variance components. We'll look at effect sizes in terms of variance accounted for in just a bit. Here's my fixed effects. So 2 new effects of interest. The others are all controlling for the effects of IQ, but otherwise are interpreted the same way. So fixed intercept 40, that's my language score for a school with average IQ, right? So centered at 0 for a student of average IQ within that school. So an average kid from an average school gets a 40. Both of these effects are significant and positive. So which one of these is the level 2 effect? I'll remind you that this means school mean IQ verbal, and this means within school IQ verbal. Which one's level 2? School mean. So for every, we have to think unit higher verbal. So this is unit higher school mean verbal. What happens to the whole school's language? Up by 7. So that's per standard deviation, although actually I'd have to look at what the distribution of the school mean is because it's not going to be a full 1. Let me check that real quick. That's why I ask for such things as part of the variable description. School mean IQ verbal has a standard deviation of about 0.5. So 1 unit is 2 standard deviations. Back to page 13. Nope, not that one. One too far. Here we are. Yeah. So for every unit higher school mean verbal, school mean language goes up by 7. Then the within school. For every unit higher IQ relative to the rest of my school, higher than my own school's average, my language goes up by about 5. Now these are both significant and they're both positive, but they're on different scales. So you have to, interpreting which of these coefficients is relatively bigger, you have to keep in mind what the standard deviation of x is and the standard deviation of y. If you wanted to think about a standardization, the standard deviation of y that's relevant would be the level 2 random intercept variance for school mean IQ verbal, as well as the standard deviation of x would be the school mean IQ verbal. At level 1, the relevant standard deviation of y would be level 1 residual variance and within school variance for this. So we can't just look at these and say, school mean matters more than within school because they're on different scales. Can you think of a way that we could talk about effect size? Dr. Aloe is going to cry if you can't answer this question. This is his life's work, you know. Effect size. How could I talk about effect size for these things? Close, not ICC. Pseudo R square, yeah, let's do that. Oh wait, I already did. So I've got two kinds of R squares here, pseudo and total. So pseudo is per pile, per variance component. Our model currently has two. It has between school level 2 random intercept differences and within school level 1 residual differences. So pseudo R square formula, which is done for you here in the macro, what it was minus what it is over what it was. It was 15 at level 2, now it's 7. 15 minus 7 divided by 15. 50%. So of the level 2 variance that remains, after accounting for the other level 2 predictors, 50% of it was explained by school mean differences in verbal IQ. That sounds impressive, doesn't it? But what do we got to keep in mind? It's 50% of what? The level 2 variance specifically, right? So that's where we would have to think back to how much variance there was there in the beginning. The intraclass correlation for that outcome was 0.2223. There we are. So yeah, so of the 0.23% that was there, 23% that was there to begin with, we explained some of it with other level 2 predictors, and we just got 50% of what's left with school mean verbal IQ. In contrast, the level 1 variance hasn't been explained yet because we haven't had any level 1 predictors. We got 35% of that with individual variation in IQ around the means. If we put that back together and just look at how correlated the predicted outcomes are with the real ones, we square that correlation. That's total R square. Previously, total R square was 3% after the level 2 predictors. It has jumped up to 39% for a difference of 36%. And I know that that is significant because here's my multivariate wall test for the 2 new fixed effects that I added. So this is equivalent to saying the change in R square. Each is significant, together they're significant. And there we have it. By the way, has any of you looked at the last page of this? You're going to like it. Do you know why? Words! Because everything that I'm saying, I wrote down for you. For 2 reasons. Number 1, I want you to like me. And number 2, I want you to be able to write your own results section someday. So this is a template because writing results is highly formulaic. So I'm navigating you through all of the models that this handout does, and we are at this section right here. So if you don't ever get all the things down that we talk about, no worries. The high points are going to be summarized for you. All right. That's where this one, here we are. I always lose my place. Okay. So, questions? Yes, ma'am.
Go to the Model 3A.
Model 3A. This one.
So it looks like the regular interpretation that we always do in the regression, like holding constants, doesn't make sense here because if I'm a kid within one school and my IQ verbal increases, that also increases the group mean. To the specific group that I stay in.
Yes,
So
your
in that case-
your original one would increase the
So
group.
in that case, I cannot hold the IQ verb bar constant if I'm going to change the IQ verb. So
Mhm.
it looks like I just don't know how do we interpret that?
In this case, by subtracting the school's mean, I have rendered this level 1 predictor and this level 2 predictor orthogonal. So you don't have to worry about saying controlling for because they're not related. Their effects would be the same if one is in the model or not. Now, if we had not done this group mean centering, if we put in the original variable, everything changes, and then you do have to worry about saying things like that because the level 2 effect that you get is going to be different if you haven't centered level 1 to remove the level 2 variance versus if you have. But right now, there are no other level 1 predictors. So in terms of explaining why some kids have better language than other kids, how smart they are relative to their school is the only thing that matters. Everything else is explaining why some schools have better average language than other schools. And those are all controlling for the other things. So this is the effect of homework controlling for everything else. This is the effect of mixed grade controlling for everything else. So that much is still true. Question?
I'm concerned about how you rescale the variables. For example, on the slides, you put the constant. And this one, you put a constant on the level 2 of homework -2.
Mhm.
But for the IQ work, you just use the mean of the level 2. And then in your example, I mean, on the slides, you put this constant there. So, but when and how? Because, for example, why you -2?
2 is near the mean. It's a variable that was
But
scaled
why
from
the
1 to
other
5.
one, you don't use any kind of constant?
Mixed grade is a binary variable,
No, I mean,
and those ones for IQ,
Yeah.
because I z-scored it.
So if you z-score something, you don't have to. So you choose either one of the 2 ways.
The mean of a z-score is 0.
No,
And-
I mean you choose either just put a constant,
Yes.
or you just standardize it.
I chose to standardize them because one of the things that I'm going to do in the next example is compare the effect of IQ verbal against the effect of IQ performance. And that comparison only makes sense if the variables share the same scale. But more generally, you'd want to center your level 2 predictors around a constant such that 0 means something. What constant that is totally up to you because it doesn't matter. It doesn't change the model fit, effect size, interpretations, other than to rearrange the parameters relative to a new reference point with respect to the intercept and main effects in the presence of an interaction.
Exactly. For homework, you don't -2. What the heck?
This fixed intercept would be different, and nothing else would change because there are no interactions.
So does it matter? I mean, in the real world.
It matters in the sense that sometimes it matters, and because sometimes it's going to matter, it's easier just to make the common practice to always center your variables such that 0 means something. It will matter more for level 1 predictors, because once you add a random slope, the intercept variance at level 2 will be conditional on the 0 value of the level 1 predictor with the random slope. And if you make that a nonsensical place, the random intercept variance may blow up. I have seen that happen before. So it never hurts to center. It sometimes helps. So I just default is 0 needs to mean something for every predictor. That's just the world I live in. Other questions? All right, then we will pick this up Thursday. Office hours start now. Let me know if you need anything.